as you want. But according to the mathematics that he discovered, Heisenberg discovered, he saw that the implication that you could measure the speed and the position both simultaneously and know them, and that they would check when you measure them again and again, was impossible. It was contra to what the theory would predict. He claimed then that it would be like this, that if you measure the position very accurately and then tried to measure the speed, or the momentum, I should say more precisely, it's the speed times the mass, then if you measure the position again, it would be different. It would be possible to have something standing still, so if you measure the speed, measure the position again and again, it's always the same. But then, if you measured the momentum, even if it's supposed to come out zero, when you measure the position, it wouldn't be exactly the same. In other words, it's not like the classical particles in a normal sense is possible only if you allow that measurements are going to disturb the system. That is, if you measure the position and then try to measure the momentum, then new position is irreversibly jiggled, if you want, by the momentum measurement. And then when you measure position, the momentum that you determined before is now screwed up. So if you measure the momentum again, it's not the same. It's completely analogous to our boxes. We measure, let's say, this and then that. We measure this. By pushing this button, it's always red. We're going to check it's perfect. We got a nice measurement of that. And now we try to measure this. Okay, we measure this and we see whether it's green, and we keep checking it's nice and green. Then we go back and see if this is still red. If it were red before, I forgot to say, let's suppose this were red. This is green. We look back, it might sometimes be green. In other words, it can change. This is a lot easier than positions, because positions can have all kinds of numerical values. Could be here or here or here or here, and here we have only two values, red or green. That's why this is kind of fun. It's easier to work with than numbers, which can have all kinds of values, and mathematics is more complicated. But here it's much easier. But you see then that the theory must predict that if you measure something, if you thought classically that there are these things under here that you're measuring, that this, whatever it is, this is the greeniness of this thing when you push 2, whatever it is, then you must allow that when you try to measure 1, you change whatever it is, the greeniness or redness for a 2 measurement. In other words, you can't measure 1 and then measure 2 and expect that it doesn't affect number 1, okay? And that's the general idea of the uncertainty principle, which more generalized says there are pairs of quantities such that if you measure 1, you cannot allow that you try to measure the other one. It doesn't change the first one, okay? Yeah, that's what I said. I meant that was an informal way of saying it changes the value. You know, right, in a way that can't be undone, that's completely lost, that the information is now lost, or partially lost.